Good day, everyone. Good afternoon, good evening, and from where you're joining from the world. Thank you so much for joining in the second session. In the second session, we're going to show you an example. It's going to be an end-to-end example on how to create a deep learning project for a certain problem that we're going to tackle that's related to oil and gas industry. And please make sure that you know that this is the last day. So if you have any question, make sure that you already have this question prepared so you can answer it after the session ends. So once the session ends, we have 10 to 15 minutes to answer some of the questions that are technical and related to the training itself. So yeah, try to make your questions as related as possible. So thank you so much. In today's session, we're going to still work on artificial intelligence, and we're going to take a look at how a neuron works. So once we understand how a neuron works, it's going to be a tiny bit easier for us to understand what the types of predictions, or let's say what the type of behavior we should get from these. So a neuron is something that's very similar to human brain. So what you see on the top is the human brain. And what you see on the bottom is the artificial neuron that human created in order to mimic how the brain works. Okay. So for example, if you want to predict something and you want to understand how something behaves, and this can be anything you want. It can be the type of the flow, the problems that you have in the field, the type of the well, the type of the event that's going to occur. So for example, you want to understand how much the reservoir pressure is going to behave, what is the PWF. Maybe you want to teach your neuron to work like Prosper, or show you predictions like Prosper, or show you predictions like Olga, or all of these softwares. So this is the main structure of the neuron. So the neuron, it's composed of three main layers, no more than that. It's just three layers, and then we expand on these. The first layer is going to be the input layer. So these layers are basically dedicated to process your input and take your input and basically make them suitable for the network. The second thing is the processing layer itself, or it's known as the hidden layer. In this layer, or in this midsection, this is where the processing happens, and all of these parameters will be weighted properly to get you the output. So this will leave us to the output layer. So the output layer is just the result layer. And if your input that's directed from left to right, it's not properly let's say predicting the output. So this is what the neuron will do. The neuron will feed back the network, and then it will tell it basically, well, modify the way you do the predictions. So basically it modifies something called weight and biases. So once these are modified, the neuron will try one more time, and it will go ahead and forward pass the data. The data will be compared one more time to the output. If it's very close enough, or there is no improvement in the result, let's say the simulation will terminate based on certain iterations we do. If not, it will go back and forth until it reaches a satisfactory result. So this is basically how a neuron works. And we said that these are the three main layers. And so this is basically how the neurons, or how the networks basically learn. So the networks basically learn based on these three actions. Number one, so let's ignore the fact that there are some inputs. Let's start from the processing. Once the processing happens and some predictions is basically obtained, you will get this prediction. And basically the neural network and the deep learning algorithm and the architecture, basically it will compare your results that you obtain from some field measurements. So it will basically a comparison between a field measurement and deep learning calculation. So if they are close enough, then we're good. And if they are not close enough, some adjustment needs to be made to the network in order for the learning process to continue. So it's basically, it's an ever evolving process. So it's basically, it's an actual a loop that goes on and on until you reach a satisfactory learning process. Okay, so this is basically, actually we have, so, but we don't, hopefully we don't need to go through all of these. Okay, so let's start building a very simple model that can predict a very common problems for us in oil and gas industry. Let me show you what we're going to predict. Let me open my drawing application. Okay, so guys, by the way, the main idea of these workshops, it's not to teach you how things are done. Obviously, it's 1 hour is not enough to teach you something that's doable, but at least you will get an idea and you will understand the work how and the think how, and basically how systematically think about solving a problem using AI and deep learning architecture. Okay, so this is an XY map in oil and gas industry. So this is known as geospatial map. So let's see what we're looking at. So on the x-axis, we're looking at x coordinates. So this can be in meters or feet, and on the y we're sorry, this is y, this is the x. So we're looking at x and y. And how did we generate this map? This map was generated based on some well location that were observed during the drilling process and the logging process. So we have locations for the wells, and these wells basically produce values for us. Each well should produce one value. By taking these wells and interpolating them over between these values, we can get such a map. Now, one of the challenges in oil and gas industry, it's how effectively you can predict the performance of the infill drilling. So in oil and gas industry, we have something called infill drilling. So infill drilling is basically whenever you want to drill a well or a certain well between existing wells. Okay, so usually this is how they know how the well is going to perform. And of course, this is going to be based on a really simplistic assumptions. Okay, so this is what they will do. So let's say that you want to drill this well, which is marked in red. So let's say you want to drill this well. This is what the experienced people do. They will basically take all the offset wells that are close by, and they will start to draw them on time scale. Let's say this is well 1, this is well 2, this is well 3. So of course, not all the wells are compared to these. They start with the same production date. That's a very known problem in the oil and gas industry. This is well 3, and let's say one final one, and let's add one more well. This is, let's say that the well 4 has never been producing. Okay, so we will discard this. And the well that you're looking for, or the well that you want to drill, is the average, or the production or the response of this well is the average of all of these wells. And it should look something like this. The act of creating this performance curve is known as the type curve. And of course, type curves are very helpful, yet they have really huge restrictions. Okay, so some of the restrictions is it's only one phase you can predict at a time. If you want to predict the reservoir pressure, it's not going to be really easy because the time is already passed. So here is another way of solving the same problem. We will create a we will create a deep learning model. And inside the deep learning model, we will input all of these wells into the model. And then we will tell the model, well, we want to drill in this location. What's the performance going to be? What's the total produced oil? What's the total produced water? And yeah, so some certain things like that. Okay, so the way I am stating this problem in a really simple fashion. But yeah, this problem can be really complicated technically, not in deep learning wise, but technically it can be really deep and complicated problem. But with enough expertise, you will be able to extract performances on any location of the well. Okay, so these problems in deep learning, these are known as geospatial problems. So geospatial problems means that these problems are related to the X and Y. Okay, so this is just one layer of the problem. Now, do you want to know what's the advanced approach to solving this problem is? There is a new technology, or there is new technique in order to solve this problem. It's known as temporal geospatial maps. So temporal geospatial maps, it means that these maps are not static. They change with time. So this is what usually you will do. You will have some certain field, like oil and gas field, okay, with certain number of wells. At each time frame, the grid, or let's say the heat map, looks in a certain way. And you will do this for like all the time frames. So each time the well locations are fixed, but the properties and the fluid movement is different. So this way you will stack all of these grids on top of each other to understand how your map is changing with time. This is known as temporal geospatial mapping. Okay, so it's a little bit advanced problem, but yeah, for now we are going to target a geospatial mapping. So let me show you what we will do. So one more time, the state of the problem is we have well locations and we want to understand what's the cumulative produced oil or what's the oil performance on any certain location that we're going to choose. Now, if you're wondering where I am going to get the data, so the data I'm going to extract the data from a database. Usually these data are not easy to find in a single place, okay? Because these data requires gathering data from different tables. And this is the query I wrote in order to extract this data. And of course, you need to care about this because I am going to provide you or show you the actual data and what it looks like. But yeah, I'm extracting this data from SQL databases. Okay, so let me show you what this will look like. Let's create a new file for today. Let's call this day2.ipym. Let's call this day2. Day2.ipymb. Okay. So let's plus on the code. This is what the day looks like. We have the well name, we have the x coordinate, we have the y coordinate, we have the total time on production. I'm showing the time in hours, but you can show the time in any unit you want. Okay? You can show it in months, you can show it in years, you can show it in days, any time you want. Total cumulative produced oil on a certain location, total produced water, total produced gas, and of course, total produced gas, basically it's derived from oil based on the PVT properties. Sometimes it's based on the allocated gas from the facility, the maximum pay zone thickness, the porosity, water saturation. By the way, you can add more layers to this, like the average oil saturation, permeability, like any heterogeneity in the formation. You can add, like, compile all of these informations. The key idea is the more information you have, the easier pattern will be detected in this type of problem. Okay, so let's start with this. First of all, we will need to import certain libraries that will allow us and facilitates the work for us. So the first thing that we need to import, it's plotting libraries. So import Plotly, Express, SPX. We will also need to import a library that allow us to read data, because in Python, to be honest, it's not easy to read data. You get libraries that will allow you to do that. Okay, so that's why we will build things as a layer. And then once you have the ability to plot, once you have the ability to read the data, next thing is you need to have the ability to build the machine learning and deep learning model. So for that, we will do import TensorFlow.keras as KS. So this is a machine learning and, so of course, deep learning model that will allow us to do some building some models. Okay, so yeah, in Python we have lots of alternatives for a single library, so we don't have to use one library. You can use multiple libraries if you want to. Okay, we will import also another part of this library, TensorFlow dot keras dot layers as ls. So we need some certain layers for like input layers, processing layers, and so on and so forth. Okay, so once we read these, we also might need from sklearn. So sklearn is a library for machine learning. In this library of machine learning, there are some certain tools that we will use for preparing the data or pre-processing the data, because the scales of the data usually it's not same, it's very different. Okay, so these are all the things we need for now. Okay, so these are all the imports. Next thing we need is to start reading the data and get some visualization to understand what we're looking at, right? So let's read the data. So data equals to pandas.read CSV. Okay, and we will pass in the name of the file, which is geospatial data CSV. and this is separated with tabs. So it's separated with tab character, which just happens to be. And let's take a look at the data. There we go. The data, this is what the data looks like. And it's exactly the same data extract from the databases. Okay? So yeah, this is what we usually do. We extract things from databases because databases are really powerful in extracting data. And then we will convert these into Python problem. So we have well name, we have X coordinates, Y coordinate, total hours on production, we have total oil, and so on and so forth. Okay. So there are few wells that we need to get rid of in this data. So let me show you how to really limit the geological the geographical coordinates. We will say that data dot X coordinates should be greater than 46, and this will basically limit our data. And let's start visualizing this. I am going to create a scatter plot for this, which is going to be our base map. So data, I will pass in the full data, and I will tell it to set the X coordinate on the X axis, and I will set the Y coordinate on the Y axis. So once we do this, this is what the chart we will get. It's a base map. All of these dots that you'll see are basically well locations. Let's modify this. Let's make sure that we are coloring these based on the total produced oil or the total oil. So basically we'll get a color scale. So the lighter the color, actually the more production you have. For example, this well has more production. The darker the colors means that the less production you have. Okay, so now we also can show the name of the well on top of these. Okay, so well name. Now we get a sense of the well names as well. We can also make sure that this map is bigger. So we will add a height function to this. Let's say that the height is 800 pixels. There we go. Now your map is a little bit large. We will insert this full map into the deep learning, and the deep learning will start to understand the geospatial patterns or the X and Y patterns in terms of production or in terms of porosity, in terms of pressure. It does not matter as long as you're doing it properly. Yeah, the value variable does not matter, but as long as you know the process. Let's move on. In order to create a model, it's really important to understand what we want to predict and what we want to train based on. Okay, so the variables we want to train on, we will call these features. And the variables we want to predict, let's call these targets. You don't have to call them these, but yeah, these are the conventions. So in the features, or what the machine learning will pick trends from, or what the machine learning and the deep learning model will detect patterns from, we're going to take a look at the X coordinate. It's really important because each well location, by the way, whenever you drill a well, the well location, it's not selected geometrically. We don't select these based on what the wells look like or what the shape of the X and Y coordinates look like. No, the well names is basically selected based on the geological features. We don't select based on geometry. Like I want this to be like X and X meters away from a certain facility. No, it's not like this. We certainly select based on the geological features we have, the geological inclusion, and we, of course, whenever we drill well, we want to maximize the recovery as well. So all of these parameters will lead to this really messy map. Okay, so let's say we want to also to take a look at the Y coordinates, and we also want to see the maximum pay zone thickness, and we need to consider these in training. And what I also want to do, I want to tell the model to take into account how many hours these wells produced, because the total cumulative production is basically related to how much hours you produced in cumulative, or how many days you produce, or any unit of time. And the target for our case, it will be total oil, but the target can be anything you want. It can be water, it can be PWF, it can be a certain pressure function, it can be, it also can be a saturation. Anything you want, as long as you have the enough input and enough output to generate the results. Okay, so these are these things. The next thing that we're going to do is, since the data, now we have multiple columns, so let's extract these. So data of features, and we will extract the Y as well. So that will be data of target. So now we have the X and Y. Let me show you what the X looks like. So this is what the X looks like. You have 4 columns, and These columns will be inserted into deep learning, and deep learning will understand the patterns between them. Okay, so this is the key idea. Why we are doing this? Because we want to predict ultimately what's the total cumulative production will be in any certain location we have in this field. Okay, so this is the key idea. For that, what we need to do is, since the data, it's so spread in scale, the scales are in some scales are in tens of thousands, some scales are in tens, some scales are in hundreds of thousands. So they to be honest, they don't really match. That's why we turn to something called scaling. Okay, so we will scale everything to make sure they are having the same scale, and the machine learning algorithm should have easier time to converge and find the results for us. Okay. And of course, this is not the only reason. There are also other reasons as well. So let's create a scalar. So let's create a standard scalar. Based on this, we will scale our x. By the way, you don't need to scale the y because you only have one y. So we will do a fit transform because we want to scale the x. And now let me show you what the x looks like. Once you scale the well, this is what the x looks like. It's between 0 and, sorry, it's between -1 and 1. So this is what the scaling looks like. So the data is really flat, and basically the scale looks very similar. That's why the machine learning can start to pick patterns between these. Once you have everything scaled up, it's now time to build the model. So the model will be based on the Keras dot sequential model. So let's build a sequential model. For sequential model, the first thing or the first layer we need, it's going to be the input layer. So that's why we're going to layers, input. And for the input layer, we need to insert the shape of the input. So the shape of the input will be depending on how many columns you want to train. So we want 4 columns. That's why you will type 4, comma. It means that I want 4 columns, but I don't care how many rows I have. This is what it means. This is our input shape. The next thing, it's going to be the processing layers or the hidden layers. So layers dot dense layers. And for the dense layers, let's start with 8 units. So 8 neurons, and then we will expand, and we will activate this with a ReLU function. The next layer will be dense layer. We will add 32 neurons, and also going to be activated with ReLU function. And we will do this a couple of more times to make sure that the network is very deep and it can pick up patterns. So layers.dense. And by the way, if you participate in the full training, you will understand all of these things, which is the dense layer, the non-dense layer, the shapes, input, the convolutional layers, the dropout layers, and all of these layers that are related to the deep learning terminology, plus what the ReLU means, what the linear means, what the softmax means. All of these things you will learn step by step once you participate in this training, because the training is more than 32 hours of training. And let's have one more layer of really deep layer, 256, and the activation is ReLU. By the way, most of the time, the activation is ReLU, but we also have other options as well. Let's add one more layer, one more dense layer of 256 neurons. So this is the number of neurons in a certain layer. So all of these neurons will fire together in order to find the answer to your problem. We'll create a ReLU, and finally, we are going to create the answer layer or the result layer, which is going to be a dense layer of just one output. If you're looking for probability, you will have multiple outputs. If you're working with multiple results, like you want to see the water volume as well, you will also do 2 outputs. But since we want 1 output, our dense layer will be just 1 output. So let's have this as well. Okay, so the next thing that we're going to do, in order to make sure that this is working properly, we will do model.compile. So we're going to compile this model. So I'm going to use a model, an algorithm called an Adam optimizer. It's basically a way to find the optimum result. Okay, so it's an approach to solve a problem. And the loss function, or the thing that I am monitoring, is called mean square error. Okay, so also you will basically, if you participate, you will learn about these errors and the metrics. For the metrics, we will have a couple of metrics. We are going to take a look at the MAPE, and we're also going to look at the MSE. Okay, so this is the model compilation. Let's run this. There we go. Now the model is compiling just fine. Now we have just one target. or one task left, start to train the model, and you will see how bad the model will be at the beginning. This is, by the way, this is a really lengthy process. Let me show you. Let's create the training process. We will say fit of X and Y, and I am going to insert the data 8 data points at a time, which is the batching size. And we will start very simple. I will iterate 50 times only. The first time I am going to do 50 time iteration. Okay. Let's run this, and we will start to get sorry, what the result will look like. So let's run this. There we go. Now these are the results from these 50 iterations. Okay, so you can see that the error was 99%, and then it jumped to 204, or the error jumped really drastically. Now let's make this a little bit longer. Let's see if this same behavior persists. Let's say that we want to take a look at 300 iterations. Let's give this a run. There we go. Now that's processing. Yeah, the error is getting smaller. By the way, you will watch two things. You will watch the loss, and you will watch the metrics as well. Basically, in this case, it's both of the same. Let me show you something. We can also plot what the training process looks like, or how basically things are improving. So for this, let me show you. We will do pandas.data frame. Let's convert the history into an actual table. So this is your performance. You have 300 data points, or you have 300 iterations. And there we go. Now this is the loss function. Let me show you dot loss dot plot. Let me show you the loss function. Now, what do we mean by loss function? It's how well your model is understanding the patterns. So the lower error or the lower loss you have, the better the converging is. Okay. So just take a look at something. We have managed in this 300 iterations, we have managed to reduce down the error from 2 into 1.2. It's like we have reduced the error like by 45%. But this is not the case in this, but we have lots of missing values, or we have lots of losses as well. That's why we will run this model for 500 more times. Okay. Now, each time you will run, it will basically start from where it left, because this is how I built the model. You can also make it start from the beginning, but I'm not doing that. This is called transfer learning. Let's click on run. Let's wait for this to finish up. And by the way, lots of times you will wait on the model to finish simulation. As long as the model is learning, it's good sign. So let's call the history function to see if it was performing this time as well. Let's run this. There we go. We have managed to reduce the error from 1.2 to 0.8. As long as you're getting this downward looking curve, it means you're good. Okay, but this is the problem. We have few data, and the pattern is not being detected easily. So that's why I am going to do 1,000 iterations this time. This is on top of the existing iterations we've done. Let's click on run. Let's wait for these iterations to finish up. We will repeat this process until we reach very satisfactory results. And I will tell you when we reach that results. So just you have to be really patient. You can see now we have something called a MAPE. MAPE is mean absolute percentage error. Let me show you the equation for MAPE so you know that. So you will get the field observation. So field data minus predicted data from deep learning divided by field data. So this is, and of course you need to multiply this by this 100%. This is known as now, since the training process stopped, you can see we have reduced our MAPE error, or the mean absolute percentage error, from 56% of error into just 14%. It means that the model is learning very, very well. But this is not always the case. If you take a look at the mean square error, this value is still high. It means that there are some losses happening in the training process. It means the model, it's picking up the pattern, but it's still not there. So if we run on the loss function, you will see, well, you're still getting improvements on training. We managed to reduce down the error by more than 100%, by the way. Let's run this one more time, 4,000. Let's run and wait for the result. The more you run this, as by the way, assumingly that you created the model properly, by the way, the more you run this, the accurate the result you should get. But to a certain level where there is no more learning happens. And I will show you when we get there, but we are still not there. Now, the average error is 13%, so we have managed to reduce the error. So let's run the loss function. There we go. The loss function is still declining. So we can keep doing this as much as possible. The more you do this, the less error you have. So let's run this one more time, just one more time, and then I'm going to show you what we will do. So we will run this for 2,000 times, and let's scroll down. Let's plus on the code once the simulation finishes up, or once the learning process is done. This is what we will do. Let's say that, by the way, this is still running. Okay, so this is still running. Let's say that we want to drill somewhere in this empty location. Okay, so let's say we want to do a drilling in this location. So in this location, we want to know what's going to be the cumulative production, or what's the ultimate recovery in this location. You will decide on the X and Y, and then you will decide on how many hours you want to operate and the predicted pay zone thickness. And the predicted pay zone thickness can be either from log data or it can be from offset wells. We will decide on these, and then we're going to tell the deep learning to tell us what is the performance of this well if we decide to predict somewhere in here. Okay. And how does it do this? Based on data-driven decisions and based on data-driven analysis. Okay, you can see it's already improving. We're already in the realm of 6 or 7% of error. So let's go ahead and write this thing. Okay, so let me just copy what the features look like. Let me just copy these, guys. So we have some reference. So these are our features. So we need X, Y, pay zone thickness, and total hours. This is for the newly drilled wells. So we are deciding on the newly drilled wells. So let's call this drilled well, or the newly drilled well, or let's call this planned well. Planned well. So the planned well will have these data of X and Y coordinates. So for X coordinate, it will be 46. Let's get some random coordinates and change them. So let's do that. So let's get some random coordinates. Let's get any random coordinates and we will change them. Okay, so this is the X coordinate and that's Y coordinate next to it. Okay, so let's change the coordinate to 8 and let's change this coordinate to 6. Okay, so we have basically created random coordinates, and let's see what the losses looks like now. There we go. The losses already improved drastically and we have only 8% of error. We can also, by the way, we can run this one more time, but not for 2,000, for 1,000, and while we're working on the remaining code. The next thing we will do, it's what's the predicted pay zone thickness will be. This can be from logs, this can be from geological maps, it can be from any source, okay? And this information is, by the way, or sometimes it's readily available, sometimes it's not, but most of the time you can find this easily if you have like the enough experience on navigating the data. Let's say the maximum pay zone thickness we have is 50 feet. The total production hours, let's say that this well can produce up to 130,000 hours. Let me show you what this equals to. So 130,000 hours divided by 24 hours, it's 5,400 some days. Divide that by 365, That's something close to 14 years of production, total production. Okay, so let's see what the performance is looking now. There we go. Now we are not getting any more improvement on the training. So there is now only 7%. I think that's it. We're going to just leave it like that. By the way, we can also do some more trainings if you want to. We can change some other parameters, but yeah, it can take some time, but definitely you can also improve the learning process. But yeah, having an error of only 7%, it's really good. It's really good, actually. Let's move on. The first one is the X, the second one is the Y, the third one is the maximum pay zone thickness available in this well, the planned well, and the total hours, it's going to be 130 hours of production. Okay, so let me show you how to predict. We will call the model dot predict, and we will predict the planned well data. We will run this. Let's see what the problem is. Let's see why this is not working. Yeah, actually, we need to scale this. I forgot that, by the way. So we need to scale this because everything is scaled. So for that, we will do planned well equals to scalar dot transform and planned well. So we need to scale this for it to become the same values as the training data. So let's see, it's called scalar. There we go. It's scalar looks good. So scalar planned well. Okay, there we go. Now let's move on. Run this. There we go. Now the model it's telling us that the well that you have projected in this location with this much parameters, with this much pay zone thickness, the well is going to produce 625,000 barrels of oil. Let me show you what that equates to. Okay, so this is the cumulative recovery from this well. And if we divide this by, if 610 divided by 14.8 years, so we are going to get 42,000 barrels per year. Okay, so let's divide this per month, divided by 12 months. So per month, we're going to get 3,000 barrels per month. Okay, and this is actually what we have already in the data as well, something similar to that. Okay, so now let's do one more thing. Now, since we know how to predict some performances of the well or the well locations, let's do something. I will create a loop where I'm going to assume the random pay zone thicknesses, and then I will tell I will tell Python to evaluate all of these to know basically how much recovery we're going to get based on these pay zone thickness. By the way, if you manipulate the pay zone thickness, the more pay zone thickness you provide, the more recovery you will get. Let me show you. If we make this 60, you will get more ultimate recovery. Because this is a pattern already picked by the deep learning, I'm not telling it how to behave. A deep learning already detected that if you provide more production hours, you will get more ultimate recovery. So this is basically something was picked up by the deep learning. That's why we trained it a lot. Let me show you what we will do. Let's do pay zone thicknesses. So pay zone thicknesses will be a list of pay zone thicknesses starting from 50 and ending at 80. So we'll assume pay zone thicknesses from 50 feet to 80 feet. And we're also going to evaluate the production. The production is going to be ultimate recovery. It's basically going to be an empty list that will populate based on the deep learning training. So we will say that for P in pays. So for each pay zone thickness that's already listed, let's construct our plan well or the new planned well. The only thing is going to be different is going to be instead of 60, we will fix the P. Okay, so we will have the planned wells. Now we will do our prediction. Okay, so by the way, you can also do something like this. So let me show you. If we do, let's do Ravel. Ravel basically flattens your data. Okay, so if you do 0, basically you will get its data. Okay, so this is how you get the actual data, because this data is two-dimensional structure. Let's do the prediction. So predicted data equals to model dot predict based on the planned well. Now we are basically moving from a single value prediction or a scalar value prediction into probabilistic modeling. Yeah, so it's very easily transformed between these. And then we will ravel this and get the only value within it, which is value 0. And of course, we will append that, sorry, or add that to our model, or to the ultimate recovery dot append. We will add the prediction to that. Okay, so let's run this. And each time we will get a prediction, we will print your current prediction is, that will be our UR. Oh, sorry, that will be our prediction. Run this. There we go. Each time you get a certain set of predictions, okay, based on the pay-zone thicknesses that you're assuming. And the pay-zone thicknesses that you're assuming is basically starting from 50 feet up to 80 feet. Now, once you get this, okay, so once you get this, you can also take a look at the ultimate recoveries, which is basically a list. And of course, if you take a look at the data as a list, you will not get much benefit. But let me show you what you can do with this. You can actually convert this into a plot. Okay, so we will do plotly express dot bar chart. We are going to a bar chart. So on the x-axis, we will have the pay-zone thicknesses, which is going to be pays. And on the y-axis, we are going to set the ultimate recovery. Okay, so this is the ultimate recovery against the pay-zone thicknesses we have. If you want, if you don't want to see as a bar, you can do as a scatter. And this is what it looks like. And of course, you can extract an equation, or you can do trend line equals to OLS to show a linear trend on this data. So this is what the data looks like. So this is a relationship between the ultimate recovery and the pay-zone thickness. This is just for the pay-zone thickness. You can do this assumption for any data range. Okay, maybe you want to do the same thing instead of the pay-zone thickness. Let's say you want to do this on the coordinate. You will move the well left or right. Maybe you want to increase the hours of production, and so on and so forth. And of course, what you can do, you can save this chart, or you can basically convert this into a table. So yeah, that's basically how you can convert a simple machine deep learning problem or a simple technical problem into a deep learning, and then you will take it from deep learning and convert it into a statistics problem. So that's all what we have from my side. Now over to you, Nikhil. I think we're ready to